In this chapter, we're going to look at the tactic monad, or metaprogramming monad. And it's called the tactic monad because it is called tactic and because it is usually used to write tactics, but not exclusively. But I don't think we're going to look at any of the non-tactic uses. So you can think of it as a monad for writing tactics. And yeah, the last chapter we stopped with this example. And before we get into the metaprogramming monad chapter, I want to talk a bit more about this example because it shows how to write a meta program or tactic, kind of in general. So the first thing you have to do is you write a meta program as a regular def, but you put this meta in front of it, which stands for metaprogram. And what this does is it disables a bunch of restrictions that lean definitions must usually obey. So for example, a meta definition doesn't have to terminate, whereas a regular lean definition always has to terminate. What this means is that in meta land you are a bit freer. You can do stuff that you can't do in regular lean, but of course, this also means that your regular lean definitions cannot refer to meta definitions. So once you have defined something in meta land, it is inaccessible to regular lean land. And this is of course necessary to provide to enforce consistency, right? Because otherwise you could just define some arbitrary garbage in meta land and then say, oh yeah, I'll use this in some proof in regular lean land. So you have to write meta, and then tactics always have type tactic alpha for some type alpha. And so the tactic indicates that we're going to operate in the tactic monad, and the alpha, which here is unit, is the return type of the tactic. So you should think of it as a tactic alpha as a imperative little program that does something and also returns a result of type alpha. And in this case, we're gonna use unit for alpha because unit is kind of the trivial type, and this tactic is not supposed to return any useful information. But there are other tactics that return useful information. So for example, there is an infer type tactic that we're going to see later, which returns the type of an expression. And so in that case, obviously the return type is something that we actually care about. Okay, and since we're defining an expression in a monadic type, we're going to use do notation a lot because it just makes defining a monadic expression much easier. And yeah, so for this expression we can actually just proceed pretty much as before, right? So here's the same definition with combinators, and pretty much what we do instead is we write the do block instead of the begin end, and then we have to write tactic dot a lot because these tactics all live in the tactic namespace, and so they have to be prefixed with tactic dot. And there is actually a way to avoid that, but we don't show you that in the course. But if you want to look that up, that's also fine, and then you can avoid this problem that you have to write tactic dot a lot. But in the course, we're gonna stick with that. And then, yeah, as you can see, you can write these individual tactics, and then you write comma, and so you can define a sequence of tactic steps. And you can see that the or else combinator that we saw in the last section is also available in regular metaprogramming tactic land. It's not just available as a tactic combinator. And yeah, these fancy apostrophes here, we're gonna talk about those a bit later, what exactly those mean. So that is the general shape of a meta definition or tactic definition, and now we're gonna go in a bit more deeply into what the metaprogramming is, what it can do, and what you can do with it. So what can you do with the metaprogramming or tactic monad? Well, in short, the tactic monad gives you access to a lot of the internal state of Lean. And what that means is you can do things like get the list of goals that are currently open. And each of these goals consists of the target, which is the thing that you're trying to prove, kind of below the line, and a list of hypotheses, which we call the local contexts, which are things that are currently in scope and that you can use to prove the target. We can also access the elaborator, which means that we can do things like type check a term or infer the type of a term, and also do elaboration. What elaboration is will become clear later. We can access the environment, which means we can look up the declarations that are currently present, like all the functions, all the inductive types that we've defined so far. And we can also do things like look at attributes, for example, the lemmas that are tagged @simp. This is not something that we will need, but can come in handy at some point. And of course, the tactic monad is a monad, as we've seen before, so we can use do notation, and it supports failure. And we've also seen that that is quite an important concept with the tactic combinators, right? So we can use the function fail to signal that a computation has indeed failed, and we can use the or else combinator to say, okay, if a tactic fails, you can try another tactic, and we've also seen that in the combinators chapter. So in this section, we're going to look at some of the kind of primitive tactics that you can use to write tactic scripts. And maybe a word of warning at this point. In Lean, there are a lot of primitive tactics, and you are not supposed to know all of them after this course. But you are supposed to know the ones that we introduce here. So when you're studying for the exam, take another look at the Hitchhiker's Guide, and I think it has lists of all the tactics that are introduced in each chapter. So you're supposed to know these. You're not supposed to know any others. And also when you're doing the homework and exercises, you can do the homework and exercises without knowing any other tactics than the ones that we present here. So let's look at some tactics that you can use. So here, for example, we're proving the lemma that 14 is even. And we can do that by giving a tactic expression directly. All right, so usually we use this begin-end block, and that's a bit of a different concept, but we can also say, okay, I'm going to give a tactic directly. And so we then start with a do block, and this whole do block has to have type tactic unit, which this do block has, because our intro and even tactic, which we defined in the last section, actually has type tactic unit. And the first primitive tactic that we're looking at here is tactic.trace, which is extremely useful because it allows you to trace, meaning just generate a message that contains whatever you give here. And so you can give all kinds of things to trace. You can give strings, but you can also give other things like expressions, lists of expressions, sets, more or less everything that we regularly use with metaprograms. You can give it to trace and it's going to print it. And so here's an example of what it does. So it generates this message here which says proving evenness ... and yeah, then it does the intro and even thing which solves the goal. This tactic.trace thing is extremely useful for debugging your tactics, which is why we introduce it so early. So if your tactic doesn't do what you want it to do, then usually the answer is put a bunch of traces in there and see what exactly your tactic is doing and why exactly that is not what you wanted it to do. Okay, yeah, as you've seen before, we can also kind of package this thing up as its own thing by doing a meta definition And yeah, we've seen this before, so I'm not going to repeat it. And then we can use that instead of the do block in the proof here. So we write by and then a tactic, and that calls the tactic and does whatever it is that the tactic does. And we can also debug tactics by using the run cmd command. So run cmd takes as its argument a tactic, in this case tactic.trace hello meta world, and it runs the tactic and gives any output that the tactic produces. So here, for example, we get the message hello meta world. Alright, here's a tactic that might be useful for your future endeavors, which is called trace goals. And essentially what it does is it prints out all of the goals that you currently have. So what we do here is like a bunch of things. So first we trace the local context, and to do that we get the local context, which is the list of hypotheses that you're currently working with, and specifically the list of hypotheses of the first goal that is currently available. And then we can trace that, because tactic.trace again knows how to deal with this type, which is a list of expressions. Then we trace the target. We can get the target with tactic.target, and then we can trace it. And then it traces the missing proofs. Here we get all the goals that are currently open using tactic.getGoals, and this gives us a list of expressions again. And then we can trace all these, and then we get the type of each of these expressions. So this is the type of the goal, and to do that we can use tactic.inferType, and we can use the mmap function, which you I think also saw in the last lecture. And we can do that to essentially run the infer-type tactic on each of the goals. So each goal is represented as an expression. We're going to get to what expressions exactly are. And so this whole thing applies the infer type to each of these expressions and collects the result, and then we can again trace that. So let's see what that looks like in practice. So here we have a lemma where we are supposed to prove even 18 and even 20. And now we first apply end.intro, which gives us two sub-goals, and then we apply the trace goals tactic that we defined up here, and then we apply the intro and even tactic, which is going to discharge this goal, or essentially solve it. One note, you'll notice here that if we write the tactic script as a do block, then we don't get this handy feature that we can look at the tactic state after each tactic, right? So here the tactic state says even 18 and even 20, even though after we apply the end.intro thing, we actually have two sub-goals. One of them is even 18, one of them is even 20. So when you write your tactics as do blocks, you kind of have to fly blind, but you can use the trace functionality to get the information of what exactly the goal looks like at each particular point in time. And so we can look at that here. So here we get the local context, which consists of the type alpha and this A up here. These are kind of useless for the lemma. They're just here for demonstration purposes, obviously. Then we get the target of the first goal, which is even 18. And then we can see here that we have two goals that we currently need to solve. They are represented as meta variables here. This is not super useful, to be honest. But the more useful thing is that down here we see what the types of these goals are. And so the type of the first goal is even 18, and the type of the second goal is even 20. So yeah, if you want, you can use this trace goals tactic when you're developing your own tactics, or of course you can, cut out parts of it. So for example here, trace the local context using this snippet, and yeah, you can define your own tracing functions, And Lean also has a couple of built-in tracing functions. I'm not sure if we show them to you. We'll have to see about that. The next thing we're going to look at is this trivial lemma. It's a trivial implication, right? We're given h of type A and we're supposed to prove A. But the interesting part here is that we get to show you within this whole big tactic script a couple more interesting tactics that you're going to need in order to write your own tactics. So one of these is tactic.getLocal, and this obtains the definition of a hypothesis from the context when you give it a name. So we're going to talk about names in detail in the future, but for now just remember that if you write apostrophe h, then this is the name h, and getLocal gets the hypothesis corresponding to that name. So we can look at the output here. We can see that h is indeed printed as h. Okay. Sometimes this sort of printing style, where an expression is like printed kind of human readably, is not what you want. Sometimes you want the actual abstract syntax tree, which we're also going to talk about in the near future. And then what you can do is you can write exp.toRaw format of h, where h is some expression, and then it's going to show you the exact expression that we have. So here, for example, we can see that the hypothesis h is represented by this little beast here. Again, I'm going to show you later what all of this means. Okay, then what we often need to do is we need to get the type of some expression, for example a hypothesis, and we do that by calling tactic.inferType with some given expression, and we get a type tau, and then we can trace tau. And let's look at the output. Okay, the type of h is A, is expected. And then, you know, A also has a type, it's a prop, so we can also infer the type of tau, and don't even know what that is. It's a mu, okay. Or nu, rather. Whatever. Yeah, we can trace that. And again, we get that the type of h, which is A, is prop. Okay. Given all these primitive tactics, we can actually write a tactic. And so what we're going to do here is we're going to redefine the assumption tactic. As you'll recall, assumption is a tactic that just looks through the list of hypotheses in our local context and picks one that immediately closes the goal if one exists. And we're gonna call our clone hypothesis, and this is gonna be a tactic unit, so a tactic that doesn't provide any useful output. And so when we define it, we're gonna start here. First of all, we're gonna get the local context, because that seems like a useful thing to do. And we bind that to the variable hs, which now is a list of expression, and you can see that when you hover here. And then we call a helper function, which is called exactList, and we call that with the local context. And now this helper function exactList, it proceeds as follows. So if the input list is empty, then that means that the context is empty, or more generally, that we haven't found a matching tactic yet, or rather a matching hypothesis, sorry. So we haven't found a hypothesis that closes our goal, and so what we then do is we tactic.fail with some error message, no expression found. Okay, so this is the edge case. In the kind of more useful case, where we have additional hypothesis to try here. So we have a context that starts with an hypothesis h, and now we can try this h. So here we first trace We say which of the hypotheses we are currently trying, and then we actually try the hypothesis and say tactic.exactH. So this whole do block is going to fail if any of the tactics in it fail. Now, the trace tactic doesn't ever fail, I don't think. But the exact tactic can fail. And when does it fail? Well, of course, if the hypothesis doesn't actually have the correct type. So, by writing it this way, well, let me put it this way. So when we write this whole tactic script in this do block, and the do block fails, then we can use the or else combinator to continue doing something useful. And that something useful is, well, recurse into exact list with the rest of the context. So essentially, in human terms, what we're doing here is this whole do block says, okay, try to solve the goal using the first hypothesis, and then the or else combinator says, if that fails, try all the other hypotheses. And yeah, this is a useful tactic. It's essentially our version of assumption, and we can apply it down here for this app of app lemma. So here we've got some alpha and some p, which is a property of alphas, and some a, and a hypothesis that says p of a, and we are supposed to conclude p of a, which is, you know, trivial, obviously. But our tactic can actually do that now. And here in the messages we can see exactly how it proceeded. So first it tried alpha and obviously failed because the target is not of type alpha. Then it tried p, then it tried a, and finally it tried h, and this closes the goal, and so our tactic overall succeeds. And we've successfully cloned assumption.